In this video, we're going to take a look at section 2.5, infinite limits. And we're going to look at how to find infinite limits, how we determine if functions have infinite limits. And we looked at them already a little bit when we were looking at continuities and discontinuities. So it should look somewhat familiar. But looking at infinite limits, there are two types of infinite limits. You have the left-handed limits and the right-handed limits. And we've already somewhat looked at these, but if I'm going to just draw a graph real quick. So for example, let's say here's our vertical asymptote. And you have a graph that comes in like this, and then a graph running out of room there. And let's say this point is at 2. 1, 2. Okay, so with left-handed limits, in this case, you have the limit as x approaches 2 from the left of this function that we graphed in red on the right there of 3 over x minus 2. The left-handed limit is going to be negative infinity. Now, that's because if you follow from the left, it's approaching negative infinity down here. Again, it's always your y values. As x approaches this, what are your y values approaching? Okay, and then our limits from the right, it's going to be, if you look at your graph, as you're approaching this vertical asymptote from the right, or this point of x equals 2 from the right, it's approaching positive infinity. Okay, so those are the left-hand and right-handed limits. And so on the left-hand limits, we would say that this decreases without bound. And that should sound familiar because before we've talked about unbounded behaviors. That would constitute that it's discontinuous. Talking about the continuity of a function. And then on the right-hand limit, we would say that it increases without bound. Okay, so then looking at the formal definition of limits using graphs to help, we're going to do that exploration in class, but just looking at this definition. Number one, you want to be able to graph each function. Oh, you know what? That's something that we'll do in class, because we know the definition of limits already with all of this. Whoops, didn't mean to scroll that out. We know the definition of limits already, but in class we'll look at kind of defining that via examples. So let's try this one, example 1. Find the one-sided limits using the graph and sketch the graph. So you're finding the one-sided limits on this. Just go ahead and sketch this graph right here. And see if you can't find that point where, in this case, it's going to be at 1, x equals 1. And then come back and see how you did. So here we have our graph of 1 over x minus 1 quantity squared. And then I went ahead and graphed x equals 1 as well, so we can see where that vertical asymptote occurs. And so if we look at our one-sided limits, you notice from the left, it's approaching positive infinity, and from the right, it's also approaching positive infinity. So when we come back here to help us to find our one-sided limits, we would say the limit as x approaches 1 from the left is equal to infinity. The limit as x approaches 1 from the right also equals infinity. So here's kind of a tricky wording that you just have to be aware of. Just because in these we say the limit as x approaches 1, or in this case 1 from the right and from the left, you notice they're both equal. And before we've determined if they're both equal, the overall limit exists. But here's the thing. Even though we say the limit as x approaches 1 is equal to infinity, so this would be a true statement, the limit as x approaches 1 is equal to infinity. Now, that doesn't mean that the limit actually exists. We're just saying that this is unbounded and the limit fails to exist for that reason. Okay, so that's kind of tricky. Just because you're saying that the limit of your function is equal to infinity doesn't mean that it has a limit. It in fact shows that it fails to exist and that it's unbounded. So if you're ever asked a question, does the limit exist, and you get something like this, you say, no, the limit is unbounded. It fails to exist, even though the limit as x approaches this c value is equal to infinity. All right, so just keep that in mind. We're not saying that the limit is infinity. We're just saying that it's unbounded, therefore it fails to exist. So now let's go ahead and define vertical asymptote here. If your function approaches positive and negative infinity on either side of an x value, then there is a vertical asymptote. Okay, so that's the definition of vertical asymptote. Again, it's as x approaches a number, y approaches positive or negative infinity. Now, how to find vertical asymptotes, right? It's very easy to find. It's where this denominator is equal to 0. Whatever function is in that denominator, set it equal to 0, and there's your vertical asymptote. So that's how you would find them. So let's go ahead and practice finding vertical asymptotes. Find in this example right here, go ahead and find your vertical asymptote. Pause the video, find it, and then come back and see how you did. Okay, so when you set the denominator equals 0, x squared plus 4 is equal to 0, then subtract 4 from each side, and there's no way you can square a number and get a negative number, so that denominator is never going to be 0, therefore there are no vertical asymptotes. Try this one. I'll give you another one here. Let's do f of x is equal to x squared plus 1 over x squared minus 1. See if you can't identify the vertical asymptote on this one. Pause the video, try this, and come back and see how you did. So here, when you set your denominator equal to 0, what I did is I broke it up because x squared minus 1, that's the difference of squares. So it's x minus 1 times the quantity of x plus 1, set that equal to 0 right here. And so you know that x is equal to both positive and negative 1, therefore we can conclude that our asymptotes are at negative 1 and positive 1. And this is helpful when we go to have to draw it analytically. We know where those asymptotes are. Now we just have to look at the behavior on each side. Okay, so looking at then going back a little bit to discontinuities and seeing if it's removable or not. So on this one, think back to removable discontinuities because sometimes they can look like vertical asymptotes. If you cannot factor anything out, then it would be non-removable and it would be a vertical asymptote. But if you can cancel things out, then it's removable. So see what you can do for this one. And we're looking at x equals negative 1 to determine if that's removable or non-removable. Okay, so here we can factor the numerator into x minus 7 times the quantity of x plus 1, and that's all over x minus 1. And remember, we set it up, it's the limit as x approaches negative 1. And you notice that the x plus 1s cancel, and you have the limit as x approaches negative 1 of just x minus 7. And we can plug negative 1 in there, and we get negative 8. That means, yes, it is removable. Sometimes the vertical asymptotes look like removable, but it can be factored out, therefore, or non-removable, therefore it can be removed. Let's look at a few more examples here. See if you can't look at these graphs. You're more than welcome to graph any of these. If you want to challenge yourself, try doing it without a graph, but seeing if you can determine whether these have vertical asymptotes or not, and where they may or may not occur. Okay, so on the first one, you could graph that and see, but you just look at it algebraically. Sometimes it's fast if you just do a little bit of thinking up front instead of just throwing it into your calculator. Because you can see we can just try direct substitution. And when we do that, we plug it in, you get 3 minus 2 over 9, which is 1 over 9. So that tells us that there is no vertical asymptote. There's an actual y value. So there is no infinite discontinuity on that one. Looking at the next one, however, it's a little bit of a different story because when you go to plug it in, you get 2 over 0. And that shows us that there's a possible infinite discontinuity. And then looking at that, I know that I can't remove it because nothing will factor out. So I know that there is a vertical asymptote or an infinite discontinuity at x equals 2. Now, what if I want to study its behavior, meaning what are the y values? As we're approaching that infinite discontinuity from the right, what are the y values doing? Are they, well, there's one of two things that we've narrowed down. Either they're going towards infinity, unbounded in the positive way, or negative infinity. And so one way we can test that algebraically, again, you can always use your graph, but I'm going to do most of what I do in class algebraically just to challenge you a little bit more. That way you can just check it on a graph. But if you plug a value really close to the value of 2, but just to the right, and I chose 2.0001. So I'm plugging in for my x values there, 2.0001 over 2.0001 minus 2, and I get this, I'm saying 0 too many times, and you get something like 20,000. That means that the limit, as x approaches this value from the right, that is unbounded. Remember, the limit doesn't exist. This is just a statement that it's unbounded, but it's headed, the y values are headed towards infinity, right? So we would still say that it's unbounded. Okay. All right. So now let's look at some properties of infinite limits, and then we'll do one more example, and then that'll be it for these notes. Now these limits are going to just make sense. If you've taken the time to understand properties of numbers and how numbers work, these are going to make total sense, but we're going to get them in writing. Now when I use the capital letter L, that just represents some real number limit. Right, and we've looked at this before. The limit as x approaches c of some value or some function g of x, that equals some real number. And now we're looking at the limit as x approaches c of some function. It equals positive or negative infinity. It doesn't really matter, just an unbounded behavior. Now, look at this first property. It says that when you take the limit of those two functions and add them together, the overall limit's going to be unbounded. Makes sense, right? Because what happens when you add any number to an already infinite value? Well, it's infinity. So again, it makes sense. And if we look at the second one, it's the product. So if you multiply a number times infinity, you get infinity. Now either of these could be positive or negative infinity, depending on the original one, if that's positive, negative. So it might help if we do positive, negative, positive, negative, positive, negative. It's not exclusive to just positive infinity. But again, there's another one that makes sense, and here's one more that makes sense. Now let's look at what happens when we divide. So this is a whole number, a real number, not a whole number, but a real number divided by an infinite number. Right, and you get 0. And we've learned that a long time ago. A number divided by infinity is always 0. Okay, so those are things that we've known to be true. Just now tying those same properties of mathematics, singing that same song we've been singing for many years, and looking at the views of calculus and limits. So go ahead and take a look at this one and determine the limits as x approaches 0 from the left of your function there. Again, try it without graphing it if you wanted to challenge yourself. So when we try this algebraically, if we just plug it in, again, this value right here, we're looking to the left of 0. So I chose negative 0.00001, but when you square it, it's going to be positive anyway, so I didn't bother putting that in there. Think smarter, not harder, right? But I put it in there. And then when you simplify it, this is going to be a number that's really close to 0. That's why I just put it as 0. And this is going to be negative infinity. So I know my answer is going to be negative infinity. Again, the limit does not exist, but we're showing that it's unbounded in that direction. And if you look at the graph, this is what the graph looks like. And it supports what we had found. As it approaches 0 from the left, it is negative infinity. And that is all for these notes. This was over 2.5 infinite limits.